This time, looking at second order step response of a low pass filter with two coincident poles. The expression that we derived previously for the case of the step response of this circuit was this one. But you can see that if P0 is equal to P1, then we've got a problem. P1 minus P0 will be 0. I've got to do a division by 0. That doesn't work. You can't do that. So all of the theory that we've worked out so far doesn't apply to the case where Q is a half and we have two poles of exactly the same value. It's a well-known problem and it tends to crop up in mathematics exams. And the solution to it is to form a general case of the solution, not in terms of e to the power of P0 and e to the power of P1, but in terms of b times t, e to the power of Pt, and c, e to the power of Pt. And those are now our three constants that we have to find, constants of the integration, and we can proceed in exactly the same way as we did before. The initial value theorem tells us that x at 0, the initial value of x is 0. And that just comes from evaluating the frequency response at infinite frequency. And the final value of the step response is 1. That comes from the final value theorem, evaluating the frequency response at DC, at 0 Hz. And we also have this result that the rate of change of the output with respect to time at t equals 0 is also 0. Substituting these into here gives us for this one that a plus c must be equal to 0, because this term would just give us 0 if we substituted in t equals 0. This one here, for infinite times, when e to the pt would be 0, bearing in mind that p is a negative number, or at least has a negative real part, that would just give us that a equals 1. So we've instantly got a equals 1 and c equals minus 1. We then apply this, and we have to do a differentiation of this, and that's slightly more complicated now, because this term here would give us b e to the pt plus b pt e to the pt, and this term here would just give us c p e to the pt, and that lot we know has got to be equal to 0. Well, at t equals 0, this term here is 0, the t would ensure that, and we know that c is minus 1, so we'd have b e to the pt minus e to the pt equals 0, p. And that's only going to happen if b is equal to p. So, those are our three values. Our final form for our step response must therefore be 1 plus pt e to the pt minus e to the pt. If I extract the factor of e to the pt, I could write it like this. And this is what it looks like. It's mostly of mathematical interest because the chances of this happening in the lab are pretty much infinitesimally small. You're never going to get values of resistors, capacitors and inductors which give you two poles at exactly the same frequency. It's just a rather irritating little case where the formulas that we can use in all other situations don't work. Now, the simulator calculates the step response from the poles and zeros in the frequency response, and if the simulator determines there are two poles at the same frequency, then the simulator does not go and try and do this type of extra calculation with different formulas. What the simulator does is increase one of the poles by 1%, decrease the other pole by 1%, and then just carry on with two slightly different pole frequencies using the same formula that it uses for every other case. The error is of the order of 0.01%, who cares? I'm mentioning the case here just to do some form of mathematical completeness. But practically, it's not that interesting a case. It so rarely happens. Okay, that's all for the low-pass filter for now. Next time, we'll have a look at the step response of the bandpass filter, where we have a 0 at 0 Hz.